I'm going to go over free response question number 6 from the 2021 AP Calculus BC exam. So for part A, we have to state the conditions that are necessary to use the integral test to determine the convergence of this series, and then we have to use the integral test to show that it converges. So let's start with our 3 conditions that we need to use the integral test. We need 1 over e to the n to be positive, decreasing, and continuous between 0 and infinity. Those are the 3 conditions that must be true in order to use the integral test, and we can now use the integral test. So we're going to do the integral from we're going from 0 to infinity of 1 over e to the n dn, and I'm going to write this as a limit. So this is the limit as b goes to infinity of the integral from 0 to b of e to the negative n, just rewrite that, dn. And now I will integrate, so integrating e to the negative n will get negative e to the negative n. I'll put the negative all the way on the outside, so we'll have a negative limit as b goes to infinity of e to the negative n going from 0 to b. And now I will plug in values. This is negative limit as b goes to infinity of, plug in b, e to the negative b is 1 over e to the b. And e to the 0 is 1, so I have to subtract 1. And as b goes to infinity, 1 over e to the b goes to 0, so this equals negative 0 minus 1. Alright, are we done? Not quite. We have to make a statement now. We have to say that since the integral from 0 to infinity of 1 over e to the n dn converges, therefore, sigma n going from 0 to infinity of 1 over e to the n must also converge. And now we're done with part A, and we'll go on to part B. So for part B, we're actually going to use this information a little bit. The function g has derivatives of all orders for all real numbers, and here's our Maclaurin series for g. And we have to use the limit comparison test with the series right here to show that the series of g of 1, so when you plug in 1 right here for x, you will get this series right here. We have to use the limit comparison test to show that this converges absolutely. So for the limit comparison test, we're going to need a limit as n goes to infinity, and we need to compare this and this. So we're going to have an a sub n over b sub n. We can make this our a sub n, so I'll put that on the top, 1 over e to the n, and I'll put this on the bottom. And since we're doing absolute convergence, we don't care about the negative 1 to the n, so I'll just write 1 over 2e to the n plus 3. And basically, we have to show that this equals some constant in between of 0 and infinity. So we'll go ahead and do that. I'll say this is the limit as n goes to infinity of 1 over e to the n, and then I'll flip the denominator and multiply times 2e to the n plus 3. Oops, plus 3. Then I'll distribute. So this is the limit as n goes to infinity of 2e to the n over e to the n. That's my first term. And then my second term, when I distribute here, is going to be 3 over e to the n. Well, these cancel out. I just have a 2. I'll take that outside. I have 2 plus the limit as n goes to infinity. Ooh, that's a little messy. N goes to infinity of 3 over e to the n. Well, as n goes to infinity, 3 over e to the n goes to 0. So this limit was just equal to 2. And I can say that g of 1 converges. I don't know if I should write down g of 1. Perhaps I should write down the sigma n going from 0 to infinity of negative 1 to the n over 2e to the n plus 3 converges absolutely, because our value here of 2 is in between of 0 and infinity, because, so I'll say 0 is less than the limit as n goes to infinity of 1 over e to the n over 1 over 2e to the n plus 3 is less than infinity. And I think this should be an okay way to write your answer. All right, now for part C, I have to determine the radius of convergence of the Maclaurin series for G. So to do that, I'm going to do the limit as n goes to infinity. And first I have to plug in n plus 1 for all the n, so I'm going to have negative 1 times to the n plus 1 times x to the n plus 1 over 2e to the n plus 1 plus 3. And then I have to multiply by the reciprocal of the original. So I'm going to have 2e to the n plus 3 over x to the n, negative 1 to the n times x to the n. And this needs to be less than 1. And now, since I'm in an absolute value, I don't care about the alternating signs. And now I'm going to group things up. So this is going to be the limit as n goes to infinity. I'm going to group these up. So I'm going to have absolute value of x to the n plus 1 over x to the n, and then times, I'm going to group these up. I have 2e to the n plus 3 over 2e to the n plus 1 plus 3. This has to be less than 1. And now I can cancel some things out. When I have this x to the n plus 1 right here, that's the same as x to the n times another x. Now I can cancel these out. And over here, the plus 3's are trivial as n goes to infinity. I don't need to worry about them. And then again, for my e to the n plus 1 is the same as e to the n times another e. And now I can cancel these out. So what's left? I'm left with the absolute value of x over e. No more limit, because I don't have any more n's, so this is basically like a constant. This has to be less than 1. And now I will multiply both sides by e. So I have absolute value of x has to be less than e. Therefore, the radius of convergence is e. All right, and now for part D, we're going to use the first two terms of the series where g for g of 1 to approximate g of 1. And we're going to use the alternating series error bound to determine an upper bound on the error of approximation. So that means I need the absolute value of the exact value of g of 1 minus the approximated value of g of 1 to be less than what I get when I have my third term in here. So let's first do our first two terms to approximate g of 1. So my first term is when n equals 0. So when n equals 0, I'm going to have 1 over 5, because plug in 0 right here, you have 2 times e to the 0 plus 3, which is 5. And then for my second term, I'm going to plug in n equals 1. So I'm going to have negative 1 to the first, which is negative 1, over 2e to the first plus 3. This right here has to be less than my third term, which is what I'll get when I plug in n equals 2. So when n equals 2, I'm going to have negative 1 squared, which is 1 over 2e squared plus 3. And this is all you have to do for part D.